Alright, so here we go. Homotopy type theory. Yesterday I was reading the chapter 1, which was about the type theory. Not exactly everything was understood, but most of it was. Next is chapter 2, which is homotopy type theory. Whatever that means. Alright, I'm just gonna read this. The central new idea in homotopy type theory is that types can be regarded as spaces in homotopy theory, or higher dimensional groupoids in category theory. Yes, of course, of course. We begin with a brief summary of the connection between homotopy theory and higher dimensional category theory. In a classical homotopy theory, I don't think I ever touched any part of homotopy before. Hopefully we don't need to know much about it. In a classical homotopy theory, the space X is a set of points equipped with a topology. A space is a set plus topology, and a path between points X and Y is represented by a continuous map, P, from 0 to 1 into X, where P0 is X and P1 is Y. Okay, this is easy to understand. This is geometry, I guess. This function can be thought of as giving a point in X at each moment of time. Many purposes, strict equality of paths, meaning pointwise equal. For many purposes, strict equality of paths, meaning pointwise equal functions, is too fine a notion. For example, one can define operations on path concatenation. If P is a path from X to Y and Q is a path from Y to Z, then the concatenation P.Q. Are we hot yet? Hello, Nerdcell. We are getting there. You see? In the very beginning. The concatenation is a path from X to Z. For example, one can define operations on path concatenation and inverses. Alright, I was wondering what this and belongs to. We can define inverses. P-1 is a path from Y to X. Alright. However, there are natural equations between these operations that do not hold for strict equality. For example, the path P concatenated with P to -1, the inverse P, which walks from X to Y and then back along the same route, is not strictly equal to the identity path, which stays at X at all times. True. Even although it's a path from X to X, it's not always at X. The remedy is to consider a coarser notion of equality of paths called homotopy. A homotopy between a pair of continuous paths, of continuous maps, F, x1 into x2, and G, x1 into x2, is a continuous map H, X, with 0 to 1 into x2. So X in this case is what? Like, this is like the space, right? We have a map from space 1 into space 2, and we have another map from space 1 into space 2. And now we have a map from space 1 and space 2, but we have like the... this is like interpolation between two functions, basically. That's what a homotopy is. It's an interpolation, Nerdsel. We know this. This is like easy for game developers, I think, to understand. Satisfying that at 0 it's equal to f, and at 1 it's equal to g. It's literally just the interpolation. It's the lerping. I guess it's not necessarily a linear interpolation, just some sort of like, well, what's it called? Like a twin, right? Homotopy. We should call it homotopy now. When you're writing code in Nerdsel and you're trying to like interpolate two things, you should call it homotopy next time. Is a continuous map. If in the specific case of paths P and Q from X to Y, a homotopy is a map 0, 1 and 0, 1 into X such that, so we have two paths. So a homotopy is a map 0, 1, 0, 1 into X such that at 0 here it's equal to point to the first path S, and at 1 it's this. For all S from 0 to 1. So this is like, this is kind of like making a 2D space, or I guess not a 2D space, like whatever you call it, like a surface. You make a surface out of two paths, I think, over here. Like, you know, if you have two segments, you like connect them together, you get like quad. It's just a specific example. Yeah, but like, I mean, the meaning of this, you know, because like in this case it's just like a general space, and in this case this space is already a part of another space which is called a path, right? So like in 2D this is a line, right? And this is another line, so we have like two lines and we like connect them together, right? Like it's easy to visualize, basically, is what I'm saying, kind of. Right, you have like one path, you have another path, and you like connect them two together, and you have like this like shape, basically, as a result. This is a beautiful illustration, right? There's a message in chat to celebrate my 3 stream streak. Congratulations, Robert Pattinson. In this case, we require also that h0t is x and h1t is y. Oh, and wait, hold on. These two are both paths from the same starting points, actually. This is not the correct example. The correct example is we have two paths which are starting and ending at the same points, right? So this is the homotopy. It's like the insides of between these two paths or something like that. Because this specifically is when they are starting at the same point. I think they like this could be in before functors. Well, judging by the this thing on the left here, we will go through the same things. We have like functions. Oh wait, functors. Hold on. This is literally in like this is going to be over there in 2.2. Functions are functors. Yes. Did you read this book already? You like the previous picture more? I think the previous picture is like more general. Like in between these two, like a general homotopy between like two maps, and then they go from two paths that start and end at the same points, but like there could be also paths that start and end at different points, and there could still be a homotopy, right? Mr. Stream, you just wanted me to write my code engine instead of finding a job. I mean, if you can do it without a job, you can survive without a job. Why should you have a job then? We need more game engines anyway, right? He didn't say game engine, he said code engine. I don't know what a code engine is. Oh, a game engine, yes. What are your thoughts on food? Is food also overrated, Nerdsaw? Well, getting enough money to have enough food to survive is not that difficult, right? In simple cases, we can think of image of the square under H as filling the space between P and Q. Yes, that's what I said. Although the general X, this doesn't really make sense. It's better to think of H as continuous deformation of P into Q. Yes, that doesn't move the endpoints. All right, this is easy to understand. Nice. Since 0 to 1 and 0 to 1 is two-dimensional, we also speak of H as two-dimensional path between paths. If you say two-dimensional path between paths, shouldn't it be called a surface? I think that's what it should be called, no? For example, because P2 concatenated with inversed P walks out and back along the same route, you know that you can continuously shrink down to identity path. Yes, that makes sense. It won't, for example, get snagged around a hole in space. Homotopy is an equivalence relation, and operations such as concatenation inverses its respected. Moreover, the homotopy equivalence classes of loops at some point x0, where two loops P and Q. Wait, so they say loops now. What's a loop? A loop is like something that starts and ends at the same point. Homotopy equivalence classes of loops at some point x0, where two loops P and Q are equated when there is a based homotopy between them. Wait, what? Where two loops are equated for like the equivalence, it's the same equivalence class. All right, equated when there is a based homotopy. What is based homotopy? Which is a homotopy as above that traditionally satisfies H0t, H1t is x0 for all t. For all t. Right side is not visible again. All right, let's just hide this. I don't know, like, if it would be nice if I could move this thing to the left somehow. I mean, I can make this a floating window, I guess, and move the window to the left, like so. Kind of annoying, though. I mean, I guess I can, instead of making this a floating one, I can just make another window like this, and it just does it automatically then. I just need to not close the window on the right. When When does a game engine becomes a game engine? When you have made a game with it, I guess, maybe. Then, like, if you made a game with something, then it's that something means it's a game engine, right? That's what I would say. So what's a based homotopy again? So what is this? H0t and H1t is x0, which means that it's stay. Oh wait, okay, I understand this. So the homotopy, the transformation, it's stay like it. The beginning and end is always at the x0. All right, that makes sense. Yeah, I can show this as an image again. This is easy to visualize at least. So basically we have two paths. Oh, I guess like, yeah, we have like two paths. They both start and end at x0 specifically, right? So like this is a one path and this is like another path. They both start and end here. And we want to have a transformation from one of them to the other one, right? But the thing is, when we're transforming like continuously from this loop to this loop, right? We can transform through a different loop, which like is over here, completely disconnected with like the starting point, somewhere in the middle of our transformation, you know? Because like, yeah, basically, like, let's say that we have like one circle and we have another circle, right? We can have a transformation which basically moves this circle like up and then down here, right? So it actually disconnects from this point. But the based homotopy says that we should always be connected to this point. This is easy. Form a group called the fundamental group. This group is an algebraic invariant of a space, which can be used to investigate whether two spaces are homotopy equivalent. There are continuous maps back and forth. There are continuous maps back and forth whose composites are homotopic to identity. Because equivalent spaces have isomorphic fundamental groups. Because homotopies are themselves a kind of two-dimensional path, there is a natural notion of three-dimensional homotopy between homotopies, and then homotopy between homotopies, and so on. Yeah, of course, that actually makes a lot of sense. And what? Three-dimensional homotopy between homotopies? Of course. Like, let's say that we have a line, right? Like, to visualize it even easier, we will say that our like initial thing is just a line, right? So we have a path from A to B, right? No, I guess it's like kind of not, it's difficult this way maybe. What about algebraic invariant? Where is, oh, this group is an algebraic invariant of a space. I don't think this matters much, understanding what this means. So these homotopy equivalence classes form a group called fundamental group. The group is algebraic invariant. I mean, what is a group? A group is something where like the binary operation has certain like rules, right? A group is a set with a binary operation that satisfies the constraint. It's associative, it has identity, and every element has an inverse element. Yes. Right? So the operation in this case of like the those are paths, right? The operation would be what? Concatenation. Identity is a path, which is just a point. An inverse is just like a path from B to A instead of A to B, and that's our group. What's the algebraic invariant? I don't know. What is algebraic invariant? Invariant theory is a branch of actual dealing with actions of groups on algebraic varieties such as vector spaces from the point of view of their effect and functions. Let's just ignore this. Homotopies are two-dimensional paths. There is a natural of three-dimensional homotopy between homotopies. Yeah, sure. This infinite tower of points, paths, homotopies between homotopies, and so on, equipped with algebraic operations such as the fundamental group, is an instance of the algebraic structure called a weak infinity groupoid, of course. An infinity groupoid consists of a collection of objects and then a collection of morphisms between objects and then morphisms between morphisms and so on, equipped with some complex algebraic structure. A morphism at level k is called k-morphism. Morphisms at each level have identity, composition, and inverse operations, which are weak in the sense that they satisfy the groupoid laws, associativity, identity, inverses cancel. Only up to morphisms at the next level. They satisfy the groupoid laws only up to morphisms at the next level. And this weakness gives rise to further structure. For example, because associativity of composition of morphisms, PQR, is PQR, is itself a high-dimensional morphism, one needs an additional operation relating various proofs of associativity. Needs an additional operation relating various proofs of associativity. The various ways to reassociate PQRS into PQRS gives rise to Maclane's pentagon. Weakness also creates non-trivial interactions between levels. You understood half of this? Yeah, I think I understood half of this too. Every topological space X has a fundamental infinity groupoids whose k-morphisms are the k-dimensional paths in X. The weakness of the infinity groupoid corresponds directly to the fact that paths form a group only up to homotopy, with the k+1 paths serving as the homotopies between the k paths. Moreover, the view of a space as an infinity groupoid preserves enough aspects of the space to do homotopy theory. The fundamental infinity groupoid construction is joined to the geometric realization of an infinity groupoid as a space. And this adjunction preserves homotopy theory. This is called homotopy hypothesis theorem, because whether it is a hypothesis or theorem depends on how you define infinity groupoid. For example, you can easily define the fundamental group of an infinity groupoid. And if you calculate the fundamental group of the fundamental infinity groupoid of a space, it will agree with the classical definition of a fundamental group of that space. Because of the correspondence, homotopy theory and higher dimensional category theory are intimately related. I only understand the two first sentences here. Sure. Now in homotopy type theory, each type can be seen to have the structure of the infinity groupoid. Recall that for any type A and any x and y of A, we have an identity type. What's going on here? We're reading a book. Hi. What's up? We're reading about homotopy type theory. Books, nah. You don't like books? This is maybe like the third book that I have been reading in my life. So I don't really like books too much either. Not sure that I have finished the first two though. The two paths P and Q. Wait, hold on. Over here. We have identity type. X is equal to Y. Also written as ID, X, Y, or just X equals to Y. Logically, we may think of elements X and Y as evidence that X and Y are equal, or as identifications of X with Y. Furthermore, type theory, unlike, say, first-order logic, allows us to consider such elements of X equal Y as individuals, which may be the letters. The reading is for glasses nerds. Also as individuals which may be the subjects of a proposition. Therefore, we can iterate the identity type. We can form the type P equals X equals Y of identifications between identifications. Sure. This and so on. The structure of this tower of identity types corresponds precisely to that of the continuous paths and higher homotopies between them in space or an infinity groupoid. Okay, sure. Thus, we will frequently refer to an element P, X equals Y, as a path from X to Y. We call X its start point and Y its end point. Two paths PQ, two paths P and Q with the same start and end point are said to be parallel, in which case an element R P is equal to Q can be thought of as a homotopy or a morphism between morphisms. We will often refer to this as a two-path or a two-dimensional path. Similarly, R equals S is the third-dimensional path, sure. If the type A is a set-like, such as a natural number, these iterated identity types will be uninteresting. But in general case, they can model non-trivial homotopy types. So the because it's a set-like, the two things are equal just because they are the same element, right? That's why they are uninteresting. See 3.1. An important difference between homotopy type theory and classical homotopy theory is that homotopy type theory provides a synthetic description of spaces. In the following sense, synthetic geometry is geometry of the style of Euclid. One starts from some basic notions, points and lines, construction and line connecting any two points, and axioms, all right angles are equal, and deduces consequences logically. Which one starts with that? The Euclidean geometry? This is in contrast with analytic geometry, where notions such as points and lines are represented concretely using Cartesian coordinates in R to N space. Lines are sets of points. You have a type theory. There are two types of people: those who used to read books when they were kids and those who like anime. Well, these types are intersecting, I think. At least. While classical homotopy theory is analytic, spaces and paths are made of points, homotopy type theory is synthetic. Points, paths, and paths between paths are basic, indivisible, primitive notions. Oh shit, Raymarch, hello. Not only I'm a businessman now, I'm also a mathematician, soon to be mathematician. I'm reading smart books for smart people, so I will become smart. Finally. Self. You know? Wow, hot. Ice cold. Which? Hello? Yeah, well, I read the first chapter yesterday about the type theory. And today I'm diving into the homotopy type theory, which is relatively easy so far. Because it's like, it's similar to geometry. Geometry is something that I think I am the most familiar with. Out of all of the maths, maybe. Like, you work with, like, a lot of geometry, I guess, when you're doing graphics. This book is too hard for you? I mean, it's difficult, but, like, sometimes I just skip things and they make sense later. I think, like, there is a problem sometimes where they are using definitions that are defined later in the book. So, like, just reading it top to bottom doesn't, like, really... isn't really the way. You sometimes need to skip through, and then you will understand something that was described earlier. Later. Moreover, one of the amazing things about homotopy type theory is that all of the basic constructions and axioms, all of the higher groupoid structure arise automatically from the induction principle for identity types. Yeah, I think this was like the most difficult thing for me, like trying to understand the induction for identities, and like, yeah, not sure if I understand it right now. Recall from 112 identity types that this says that if for every x and y of type A and every p, which is proof that x is equal to y, we have a type D xyp, and for every A, type A, we have an element D A of this type, then there exists an element oh, this is how we define the induction for like identities. Yeah, yeah, this one is the most difficult part, I think, so far of this book. But basically, why are you reading this? Are you designing a type system? I'm making a programming language, so kind of, yeah. I don't even know what that formula is read with precedence. Is this the implication in the product or not? This? Alright, Ray March, since you were not reading this book with us yesterday, this is just a function. This over here, an arrow is just a function. So like A into B is just a function from A to B, right? The P operator is also just a function, but this function is different. So this is a for all. For all x and y of type A, you have this, right? And a for all is not different from a function. The only difference from a function is that you use the arguments to this function to define the result type, which is why this is called a dependent function. So you could also, let me just maybe do this here. It's easy. So this is for all x and y of type A, x and y into u, right? So this is basically the same as, you know, you have arguments x and y of type A, and then as a result, you get this thing over here. X equals to y is also just like, it's just a, like, it's basically a type ID x and y, kind of. And this returns u, right? So this is the function. The reason this symbol is different is because, like, it's a dependent function. The type, the resulting type of this function depends on the values of the arguments, right? This binds stronger than p. Yeah, I guess it does. Right? Yeah. There's also some of the things. This U over here, for example, has been used a lot. U is the universe. A universe is a type of a type, so this is just a thing that returns a type. Basically, that's how we write it in cast. For example, this is a type. This is associative. Yeah, this is the right associative though, like this. It is right associative in languages like Haskell too. I mean, that's just how it works, right? Yeah, it's right associative. And then, like, also one of the other really good ideas from earlier. Yeah, impossible to read. You hate the pi operator. Yeah, I don't like it too much, but it's basically a for all. So, like, in cast, for example, since, like, we do this, we would say for all x and y, and both of these are of type A, right? For both of these, we have a function which is id x and y returning a type. This is how I would write this in cast, at least with the current syntax, I guess. And I don't really need to do this. This could be inferred, I guess. SQRT did it try? They added a huge line at the top. Yeah. They actually have like multiple different things, multiple different notations that you can use. This is just one of them. Okay, so here's the really interesting part about this book so far, though. This is called propositions as types. So we want to prove things sometimes, right? For example, when you're writing your thing, you say something like you know, in Rust, you can have wait, can you have it in Rust? Like, you have a function foo, a and b, where a is equal to b. Can you do this in Rust? I'm not sure. Logic. So you need to check this or like some other things in your programming language, right? So this is something that needs to be like proven, right? So we so that's why a is equal b. So this is where we get to the thing where propositions or something that we want to prove is a type, and then an actual proof of that fact is the value of that type. So if we have if something is true, then we have a value of this proposition, basically. That's the nice idea. So when you have like a function from a to b, for example, if a is true, then you have the value of a. And if you have a value of a, if you have this function, then you also have the value of b, because you can just apply the function, right? Which means that this can also be read that if a is true, then b is also true. So it's just an implication in the logic. And then similarly to that, the P or for all means like literally just for all something is true, and then the dependent pair types is something that says that if there exists a thing such that something is true, and like similar to that. It's nice. Someone is reviewing my code. Yeah, I need to take a quick break for like 5 minutes. But I think propositions as types was like the most interesting and useful thing from this book so far for me. Mm-hmm. Do you have future projects in mind already? Nothing. You'll get plans. Yeah, Remarch said that he's going to quit. Shame is the last project. All right. You should quit quitting. Okay. All right. So this over here is a little bit confusing, but here's the basic idea, right? So we have types, propositions as types, and basically if you have a value of a type, then you have a proof that the proposition is true, right? So this over here is a function a into b, right? And a into b means that if a then b in terms of logic, right? So how to prove that if a then b? In order to prove that, all you need to do is to have the value of this type, and the value of the function type is just the function. So if you can write the function which has this type signature, then you automatically have proof that if a then b. That's the nice thing. And then this ID is basically this type over here, right? ID xy, or otherwise written as x equal y, is the proposition that x is equal to y, right? So how do we prove that two things are equal? In order to prove anything, we need to have a value of the type representing the proposition. So this is the type representing the fact that x is equal to y. Okay? So when we have a value of this, we have a proof that x is equal to y. Right? So that's how we read this thing here. This basically means here that if we have proven that if we know that x and y are equal, then something else, and we also have proven that that this is true for the simplest case where x and y are the same thing, right? A and a. What is this returning? This is anything. This is u is any type, and any type represents any proposition. So we are like it's like U doesn't mean it exists. No, U is the universe, which is the universe of all propositions. So like this is some concrete proposition, which we don't know what exactly the proposition is, right? But we know that we have proven something, right? It depends on the actual like function. What exactly are we proving? We don't know what exactly we are proving, but if we have proven that this is true if x and y are equal, and we have also proven that this is true for the simplest case of this, where x and y are literally the same thing. So where if x equals to x, then u, then we have also proven like the entire thing, kind of. This is a little bit difficult to understand, though. Yeah, this is the most difficult part of the book so far, I think. But it makes sense, kind of. So if we are given this means that we have already like basically proved something, right? Because if we have this, if we have a value of this type, then we have proven this, right? Because type is a proposition and a value of this type is a proof, right? So if we have proven this and we have proven that, then then it means that we can also prove this, right? the induction principle, and the induction principle says that for like, it doesn't matter how we know that x and y are equal. It doesn't matter how exactly we know that x and y are equal, but if they are equal, then we are like, but for all of the x and y's that are equal, this is true. So I prove to me in uni, you have proven something. Usually every time we apply this induction rule, we will either not care about the specific function being defined, or we will immediately give it a different name. Informally, the induction principle for identity types says that if we want to construct an object or prove a statement, right, which depends on an inhabitant P, which is of an identity type, then it suffices to perform the construction in the special case where x and y are the same judgmentally, and P is a reflexivity element judgmentally. Then writing informally, we may express this with a phrase such as, by induction, it suffices to assume. This reduction to the reflexivity case is analogous to the reduction of the base case and inductive step in an ordinary proof by induction on the natural numbers. And also to the left case and right case in a proof by case analysis on a disjoint union or disjunction. The conversion rule is less familiar in the context of proof by induction on natural numbers, but there is an analogous notion in the related concept of definition by recursion. If a sequence AN, where n is a natural number, is defined by giving a0 and specifying an plus 1 in terms of an, then in fact the zeroth term of the resulting sequence is the given one, and the given recurrence relation relating an plus 1 to an holds for the resulting sequence. This may seem so obvious as to not be worth saying, but if we view a definition by recursion as an algorithm for calculating values of a sequence, then it is precisely the process of executing that algorithm. Non-codes, hello. We are reading a book. The book is hard. The book is smart. It's not as smart as we are, unfortunately. I don't know if there is any person in chat who is understanding the entire thing here. We're trying. As given, it gives what gives it, huh? This may seem obvious. Alright. It gives hot. The rule is analogous. It says that if we define an object f p for all p x y, hold on, the rule is analogous. It says that if we define an object f p for all p, which is a proof that x is equal to y, there by specifying that the value should be what the value should be when p is a reflection, which is a proof that x is equal to x, then the value we specified is in fact the value of f refl x. Yes. What's the topic? It's the homotopy type theory. So I'm making a programming language, so I'm diving deep into the type theory and stuff in order to make my own programming language to be better than the others. We need to be smarter than the others, so we're reading all the books in existence. In simple terms, we don't know, like, but okay, so homotopy is basically like geometry kind of thing, you know? So like when you have a programming language, you have types, right? So that's what we're studying here, types, right? So what is a type? A type can be seen as multiple things. For example, a type can be like basically like a set of like proper values, right? So you can see types as sets, right? That makes sense, right? You can see types as sets. For example, a type of integer is the set of all integers, right? And a type of a boolean is a set which has two elements, a true and a false element, right? So the homotopy type theory is, instead of thinking about types as sets, says that we should think about types as spaces in like the like whatever space means, you know. So space, like in geometry, like for example, a 2D plane is a space, right? Which is also kind of a set, right? So like a 2D plane is like a set of all points, right? So they're kind of very similar, sets, spaces, everything, but it's like different branches of like mathematics, I guess, or something. There's also logic, right? Which is another thing. So we can think of a type as a set, we can think of a type as a space, or we can think of a type as a proposition when we're doing logic. And we have an element of a type. So like say the type is an integer, and this is some concrete integer like 1 to 3, right? Then we can also think of it as an element of a set, or we can think of the value of a type as a point in space. Or if we are doing logic, then we can think of a value as a proof of a proposition, right? So these are all the different like meanings of types that we're studying. But a space is a set. Well, it's like not exactly, like a space is different from a set, because what? Hold on, let me refresh my memory. What's the difference between spaces and sets? It's not exactly the same thing, right? A space is a set, but it's not just a set. It's a set equipped with topology, right? That's what it is. And what is a topology? I don't really know what a topology is, but it's not just a set, you know? It's a set plus a topology. So yeah, one thing when we think about types as spaces is that we have the notion of paths now, right? Which is like an interpolation between two types, kind of, right? A function from 0 to 1 into x, where x is space or like type, since we're studying types, right? We can interpolate between two types. So can they traverse the topology? Is there like gradient descent to fall into proof? Maybe, I don't know. Like I only just started. Like I'm like the homotopy specifically. I'm just in the very beginning here. But maybe we can do some gradient descent to fall into proof. Maybe. Okay, where was I? We were here, right? The yeah, we have that. So by induction. The conversion rule is less familiar in the context of proof by induction or natural numbers, but there is an analogous notion, definition by recursion. So when we define something by recursion, sure. The induction principle endows each type with a structure on an infinity groupoid and each function between two types with the structure of the infinity functor between two such groupoids. This is an interesting from a mathematical point of view because it gives a new way to work with infinity groupoids. It is interesting from a type theoretic point of view because it reveals new operations that are associated with each type and function. In the remaining of the chapter, we begin to explore this structure. So, like, there is not everything that I understand here. Not all of the... Like, for example, they use the word functor here, right? But they have not defined it yet. The functor is going to be defined in 2.2 here. This book is done for mathematicians, not for programmers. I wish there was, like, a book like this that was for programmers instead, you know? There's too much math happening. This is giga brain stuff, yeah. I don't think, like, so I think it's not actually that difficult. It's only difficult because we are not mathematicians, you know? That's the only reason. Like, it's just like the language that they use here. If it was a different language, it would be easier for us to understand. As programmers. Welcome back, Nerdsoul. At least it's nicely formatted. Well, I mean, this is not the hardest book ever. That, like... I mean, it's not that I have read a lot of books about math, of course. But, like... There is not too much prior knowledge. They do define, like you joined today, right? But I was reading this yesterday, so like a lot of these notions they actually define before they use it. So like even although you look at this, what the fuck is P, right? And what does this mean? But they actually define all of that earlier. We were reading through this yesterday, what this means exactly and how to read this. Alright, types are higher groupoids. We now derive from the induction principle the beginnings of structure of a higher groupoid. We begin with symmetry of equality, which in topological language means that paths can be reversed. For every type A and every x and y, there is a function x equals y into y equals x. There you go. Like, this is easy to understand, right? We basically... What? Is this a lemma? What is a lemma? A lemma is something that we need to prove, or what? What is a lemma even? And it's an intermediate theorem, so it's like, it's also a theorem. Alright. What's the difference between a theorem and a theory? I don't know. Theory provides ways to explain, calculate, and explore a subject. A theorem is a conclusion derived from accepted truths. It's like a useless theorem. So we want to prove that if x is equal to y, then also y is equal to x. That's what we want to prove here, right? And this is denoted as p into p negative 1. This is the arrow which is defining a function, not the function type, but the... not defining the function type, but the function, like, itself, I guess. Such that p... Oh, wait, hold on. Denoted this, such as that raffle x, negative 1 is raffle x for each x. So raffle x is basically the proof that x is equal to x. So the negation, so the inverse of x equal to x is the same x is equal to x. You can call p negative 1 is the inverse of p. Since this is our first time stating something as a lemma or theorem. Oh, I was literally asking what it is, right? See, they actually explain these things. The only problem is that they explain things after they use the word. So they use the word lemma, and then they explain what the fuck is lemma. That's like what is confusing about this book sometimes. Would it be nicer if they describe what it is and then use the word? Recall that propositions are identified with types, where lemmas and theorems, statements that have been proven, are identified with inhabited types. Hello, Devninja. In every other math context, I would assume the right arrow binds stronger than P, because arrow is kind of like equals, so no sane person would have equal bind stronger than P. I mean, this is the big P, not the small p. Right? Maybe that's the difference. Similar to sigma. Yes. There is also sigmas. We have not seen this here yet, but sigmas are also here. They are important. So P is basically F for all, and sigma is it exists. Kind of, when we're thinking about logic, at least. We're in about lemmas and theorems here. Sigma has the same problem. I don't know. I'm not doing much math, so I don't know how you usually like. What's the usual priorities here? But the priority is that they are right associative here. So, like for example, this here we have two p's, right? So technically, all of this to the right side is like inside parentheses of this. So it's like a function from a to u into this kind of. Is this math? Yeah, it is. So according to the interpretation of the universe and quantifiers for every, the type corresponding to lemma is this. So yeah, here you go, right? So we want to prove this lemma, right? So what we need to do to prove a lemma, this is a type, right? Or more specifically, this is a type, right? Because x and y are not defined here for every x and y, and this means for every x and y. So this is the type that we need to construct somehow, and if we can construct it, then we can prove the lemma, basically, right? The proof of a lemma will consist of constructing an element of this type, which means deriving the judgment for some f. We introduced the notation minus 1. What? For this element f, in which argument a, x, and y are omitted and inferred from the context. Like, for example, this one. I don't know how, so like this sigma, it's only summing up ij, this thing? Or is it summing up ij and this? I mean, there's I here, which means that this belongs to inside of the sum, right? Otherwise, it wouldn't make much sense. So we have given the y and j here on the outside, and I is inside of the sigma. Given the equality. Yeah, the equality is a different equality, yeah. It's not an equality. It's the different notion of a type, yeah. The equality is weird here, yeah, I agree. But like I was saying over here, right? This is what we're trying to do. We're trying to prove that x is equal to y. So this is just basically x equals to y is a syntactic sugar to the type ID xy, kind of, right? But since the meaning of ID xy is that x is equals to y, that's why they choose to write it like this. So it's not exactly like equal in the normal like sense of this thing. But they put it in parentheses anyway, yeah. The secondary statement, raffle x -1 is this, should be regarded as a separate judgment. First proof, assume given a, u, and let d is for all x and y of a, x is equal to u, then u, be the type family defined by d, xyp, is y equals x. Is type theory a thing in most programming language? I assume it's for your language. What do you mean it's a thing in most programming languages? I mean, you don't need to understand the type theory to program. No, you don't.
Like most programming language, they don't even have dependent functions or dependent types, right? And other than dependent types and dependent functions, which is literally these for all and exists things, kind of, all that they describe in this type theory is basically just normal functions, a product type, which is like a tuple, and like, I don't know, like Boolean coproduct type is like an enum, a sum type, right? I don't know, you don't need to understand type theory. This kind of math gives me headache. Too many unknown characters to you. Well, I mean, I'm reading the middle of the book right now, not the beginning. This is now known to me. I have read what these symbols mean. You know? You know what a lambda is, right? A lambda is a function with argument x, which returns raffle x. There you go. So this, we are defining function d, which returns for each x a raffle x. Whatever raffle x means, right? But the type of this function is for all x of type A, so like this x is of type A, right? And the type of raffle x is d xx raffle x. That's easy, right? Reminds me of Haskell's for all. Yes, this is Haskell's for all. This is like I mean, yeah, we also have for all in cast. So in general, a for all is just corresponding to a dependent function. How's my programming language going to be different? Well, it's just going to be better than everything else, you know? So like all the languages suck, and we need to make a better one. So it's going to be a good one, finally, you know? But I don't know how many programming languages you tried. So the reason we're doing it into the theory here is because so like a lot of the problems, a lot of the bugs in code, they are because of the like implicit assumptions about the code, kind of. So we want to make more things instead of implicit to be explicit, so that when you read an API, you understand how to use the API. You don't need to like do assumptions. For example, you call a function and a function can fail, right? Like let's do like simple example. The simplest example would be something like function square root of x, right? Which is like an integer or something. I don't know, a floating point number, right? Whatever. So this function, it can fail, right? But when you look at the function, it doesn't really say that it can fail, right? You can just assume that you can just use the square root for all the numbers, but it doesn't work for negatives, right? So we want to fix that, kind of. But this is like the simplest example. So we want to be able to tell as much as possible to the compiler so that it can like prove that our programs are correct, so that I never on accident call the square root with a negative number, for example. Right? That's the simple example. So like similar to that, there is, for example, just a like dynamically typed languages versus statically typed language. So like we can also write this function as square root of x, right? And when you look at this, what the fuck is x? What am I supposed to pass to this function? Maybe I should pass it a string, and then your program will crash. So similar to how like static type systems fix these simple like things, right? Where you don't need to like assume or like read documentation which is always like out of date or something, right? You actually enforce the fact that you can only call the function with like a correct type. And then what is the correct type? Is the correct type for the square root just like a number, or is it like something more precise even, which is like a non-negative number, right? So it's like we're trying to not just make a statically typed language, but like the like uber typed, or I don't know, super typed. Everything should be like as much as possible should be like written down formally, kind of. With Rush data, I don't see nerds to be in an extremely weird spot. They have distinction between unit and int. Oh, uint and int. But anything that goes further, they reject. Well, when you want to do something more complex, it like this comes at a cost, of course, right? When you want to say that x is not just a floating point number, but it's a floating point number that is like more than 10, not just a non-negative, right? It's more than 10, for example, for some other function. This complicates the type system for sure, right? So, I mean, it is kind of a trade-off, right? So C is trying to be a simple language. And a lot of languages are actually trying to be simple language. But because they are so simple, they cannot describe certain like properties that would be nice to know about your program, and you end up like assuming things. And assuming things leads to bugs. They will argue that style of NPI with vec3, etc. But for numbers, they don't do that. Like, then why not just go full type erased and say everything is a chunk of bytes? It's up to dev to write descriptive code. Well, yeah, also like the good thing about if you have a good type system is that you don't actually need to write code. All you need to do is to read kind of like the type, right? So you don't care about the implementation details, right? You only care about the type. Like going back to this example of the square root, obviously if you see this function and you are wondering, like, can it be any floating point number that I can pass as an argument? Well, you can just see the code and it says like if x is less than 0, then panic, right? So you can look in the implementation of this function, and because you have read the implementation, you now know that it's not just any floating point, it's a non-negative floating point, right? But this means that you need to look into the implementation to actually understand what the function does, and it's not always as simple as just being the first line in the code, right? So if this is instead done on the type level over here, this is much better, because then you don't need to look at places, and also it's better because it can be like checked by the compiler. What's this? Oh, so this is like this sum. Function square root non-negative number. Yeah, I mean, this is good, yeah, so like good naming also helps a lot if you say over here non-negative, right? But this is a simple example. Remember that this is just a simple example of something being non-negative, right? This is the simplest thing ever. It's not always as simple as like non-negative. There may be like a lot of restrictions there, and like transitive restrictions or something. Solving a real problem. I mean, yeah, this is nice, I guess. Maybe, I don't know. I mean, the syntax doesn't matter too much, though. for me personally. You just need to learn the syntax. It does when it's ambiguous. Well, the only reason it's ambiguous is because you are not used to the rules, like in this book or something, right? I mean, you had 2 papers in uni that interpret sigma differently. Yeah, I mean, maybe in this book the sigma is also different because sigma is not like sigma is usually used for summing things up, right? But this is not a sum. This is the dependent pair, and actually, here's the definition of the syntax. There is three different ways you can write this. So you can write a sigma xa bx, or you can write xa underneath the sigma, or you can write x like just on the same line and with a comma. There's like literally 3 different ways to write the same thing. All right, I'm gonna need more. Because I don't have a lot of time today, actually. So I don't know if I can read the entire 2nd chapter. This is our first time starting the lemma. So yeah, the lemma, to prove it, is constructing the element of this type, which is just defining this function. We have, in other words, these function, something, we have this element for x, reffle x, of this type. First proof, assume given a, u, and let d is for all x and y of x, x equals y into u, be the type family defined by d, x, y, p, is y equals x. All right. In other words, d, a function assigning to any x and y, and a proof that they are equal, a type, which is this. Sure. Did you see that Firefox got tab groups? Like Chrome has for ages? No. I have the containers, but that's a plugin, which Chrome doesn't have, I think. Is there a plugin for Chrome for containers? I think last time I was checking there was not. The induction principle for identity types gives us the element induction. Y is equal x for each p, x equals y. We can now define the desired function a minus. What was this again? We introduced the notation minus 1 for this element f. In which the arguments are omitted and inferred from context. Okay. Sure. So f is just this. The element of this type, this function. All right. We can now define the desired function. -1. Why is it like even like why is this used as a notation? Shouldn't this be like equals -1? Because the what this is doing is that it is proving that is if x is equal to y, then y is equal to x. Why are they using the this symbol instead of the equality symbol? Because this is what inverses the equality, right? Weird. Anyway. So we can now define the desired function to be lambda p. So using the induction, If we have proof that x is equal to y, then we oh, it returns the type y equals x. Okay, yes, of course. Yes. Okay, yeah. So basically what this is that because we have the induction principle and we have proven the this fact for if x is equals x, then x is equals x, using that we can now prove that if x is equals y, then y is equals x. Because we have the induction. We have written out the proof in a very formal style, which may be helpful by the induction rule on identity types is unfamiliar. To be even more formal, we could say that lemma 2, when one is proved together, it consists of the judgment this. Inferred from context is like whatever I said before. Even more formal. So for all, I mean, this is the type and this is the value. I'm wondering if they don't do this. Why don't they do this in math? So like, when we are writing programs, right? They could have specified over here the type of A, right? A is U over here, right? So like, I think this is making it like a little bit more difficult to parse, right? Where you need to match the type here to the type here, instead of having the types being in line, you know? But I don't think they ever do this. Along with the Nash, the additional equality judgment. The p y is equal x. Yes. Okay. Yeah, so this is proof by induction. This over here is the induction rule. This is the like initial proof for the simplest case, which is the reflexivity where x is equal to x, and then using that we can we are basically automatically constructing the thing. So the induction is like this helper function. You don't understand how induction works here? So like, you understand, like the induction rule depends on the type. In this case, the type is the equality, right? That's what I'm saying. Like the induction for equality is like the most difficult part. But the way it works is that it allows us to prove more complex things from the simpler things, right? So in this case, since we're trying to prove that if x is equal y, then y is equal x, right? We are using the induction given the initial thing over here. This over here, lambda x, reffle x, right? This is the simplest case where x and y are the same thing, which means that if x is equal to y, then if x is equal to x, then x is equal to x. This is what this is here, right? This is proof for the simplest case, right? And this is what we are trying to prove, basically. So what we are trying to prove, how do we prove it for the simplest case? And then we just give the arguments to this thing in order to actually prove it. But like the actual implementation of the induction is what's doing the magic here, right? I mean, it's kind of making sense. But like, I guess the difficult part here is understanding the implementation of induction. However, eventually we prefer to use more natural language, such as the following. equivalent proof. Second proof, we want to construct for each x and y of type A and P, which is proof of x equals to y, and an element P to -1, which is y equals to x, right? That's what we're trying to do, right? So we are trying to prove that y equals x, which is making an element of this type, given the proof that x equals y. So this is proof. Right? If we have this proof, we want to find this. By induction, it suffices to say to do this in the case where y and x, y is x and p is ref x, right? So like we are using induction, so it suffices for us to do this in the simplest case. But in this case, the type x is equals y of p and the type y is equal x in which we're trying to construct are both simply x equal x. So it is ref x -1 is simply ref x. So the general case then follows by the induction principle, and the conversion rule is precisely the proof in the reflexivity case that we gave. We will write out the next few proofs in both styles to help the reader become more accustomed to the latter one. When next we prove the transitivity of equality, or equivalency, we concatenate paths. Yeah, so now, if like we have proven that if x is equal to y, then y is equal to x. Now we want to prove if x is equal to y and y is equals to z, then also x is equals to z, right? This transitivity. So once again, I think this is, I don't know, what is the simplest case here? We also do it by induction. Note that we choose to notate path concatenation. I guess the simplest case here would be that that x and y are the same thing. So basically, if we know that x is equals to x and x is equals to z, then x is equals to z, right? Which is obvious. So we like that's how we prove it for the simplest case, and then yeah. And then by induction, it just works. Let me see what they write here. So instead of dividing function equivalent type, which allows us to apply the path induction twice. Hold on. The desired function has this type. Yes. We will instead define a function with the equivalent type, pay xy. Yes. Yes. It allows us to apply path induction twice. db roll x and y. X, y, u be the type family. Roll z. Oh wait, no, wait, yeah. Know that x reflex is for z. If x equal to z, then x is equal to z. Yes. So in order to apply the induction principle for identity types, then we need to define a function, which is to say of type yes. So this is just returning q as is. I'll let e be x, z, a. U be the type family, which says that x is equal to z. Know that e for x as ref x is x equals x. Yes. Wait, they applied the induction twice? I thought it would be like easier to do this the way I said it, no? By induction principle for identity types applied to E, we obtain a function D. But E exec is equals the, so the type of D is this. Thus, we can use the function D and apply the induction principle for identity types to D to obtain our desired function of this type. And hence, this. The conversion rules of the two induction principle gives us a raffle x. Raffle x is the same as raffle x. Yeah. Yeah, but I think like, yeah, they do it in a little bit of a different way here than I said. Second proof, we want to construct for every x, y, z, a, and every p, x and y, and y, z, an element of x is z. By induction of p, it suffices to assume that y is x, and p is reflex. In this case, the type yz of q is x equals z. Yes. Now, by induction on q, it suffices to assume also that z is x. But like, so here's the thing, right? Why are they doing the double induction? Isn't this already like enough? Like, if we know that q is x equals z, right? Like, we don't need double induction here, since like we already have over here, if we have x is equal to z, and we want to like get the x equals to z, we just use the identity function here, right? Like, why do they need a double induction? It's weird, but okay. The reader may well feel that we have given an overly convoluted proof of this lemma. In fact, we could stop right after the induction of p. Oh, there you go. Since at that point we want to introduce an equality xz, and we already have such an equality named q, why do we go on to another induction on q? Yeah, there you go. So the answer is, as described in the introduction, we are doing proof-relevant mathematics. When we prove a lemma, we are defining an inhabitant of some type, and it can matter what specific element we defined in the course of the proof. When we prove a lemma, we're defining an inhabitant of some type, and it can matter what specific element we define in the course of the proof, not merely the type inhabited by that element. The lemma has three obvious proofs. We could do induction over P, induction over Q, or induction over both of them. If we proved it three different ways, we could have three different elements of the same type. It is not hard to show that these three elements are equal, but they are not definitionally equal. There can still be reasons to prefer one over another. Okay, so basically they are saying that we can prove the lemma in different ways, and in our system here, the way we prove things can matter, because we are using like propositions as types, and like evidence, and like the elements of this type is like the proof, actually, right? The evidence that we use to prove other things, which is like a value of the type representing the proposition. Like, it depends what element we choose. Depending on what proof we used to prove a thing, we may prove other things like easier or harder, I guess, right? That's what this says. So even although we have three obvious ways to prove this thing, we might want to use one or the other. In the case of lemma, the difference hinges on the computation rule. If we proved the lemma using a single induction over P, then we would end up with a computation rule of the form raffle Y Q is Q. If we proved it with single induction over Q, we would have instead P raffle Y is P. While proving it with a double induction, as we did, gives only raffle X, and raffle X is raffle X. People say regex is black magic, but they never saw university math. The asymmetrical computation rules can sometimes be convenient when doing formalized mathematics, as they allow the computer to simplify more things automatically. We did formal regex in uni with Mach notation. I'm sorry. However, in informal mathematics, and arguably even in the formalized case, it can be confusing to have a concatenation operator which behaves asymmetrically. And to have to remember which side is the special one. Treating both sides symmetrically makes for more robust proofs. This is why we have given proof that we did. However, this is admittedly a stylistic choice. So yeah, I was having the correct solution, but they are different solutions a little bit. The table below summarizes the equality, homotopical, and hierarchoid points of view on what we have done so far. Equality. So equality, it has the property of reflexivity, symmetry, and transitivity. Reflexivity means that x is equal to x, so this is a constant path, a point, right? Symmetry means the inversion of paths, so a path from x to y becomes a path from y to x, and transitivity is concatenation of paths. So if we have a path from x to y and a path from y to z, then we have a path from x to z. All right. In practice, transitivity is often applied to prove an equality by a chain of intermediate steps. We will use the common notation for this such that A is B is C is D. Sure. So yeah, see, they are introducing the notation where they are all equal to each other. If the intermediate expressions are long, or we want to specify the witness of each equality, we may write this. This is equal by P, so this is equal, this is a type, and this is the proof of this. Yeah. In either case, the notation indicates the construction of the elements P, Q, R, which is the fact that A is equal D. We choose left associativity for correctness, although in view of lemma below, it makes little difference. It should happen that B and C, if it should happen that B and C are judgmentally equal, then we may write just this. Yeah, because judgmental equality is like different. Okay. We indicate the construction of PR, A and D. We also follow common mathematical practice of not requiring the justification of this notation. By P and by R to supply the exact witness needed. Instead, we allow them to simply mention the most important part, or least obvious ingredient in constructing a witness. For instance, if lemma A states that for all x and y we have fx is equal to gy, then we may write
by lemma A as a justification for the step fa is gb, trusting the reader to deduce that we apply lemma A with x is A and y is B. Sure. Yes. We may also omit justification entirely if we trust the reader to be able to guess it. Guessing things? How about not? Now, because of proof relevance, we cannot stop after proving symmetry and transitivity of equality. We need to know that these operations on equality are well behaved. This issue is invisible in set theory, where symmetry and transitivity are mere properties of equality rather than structure and paths. From the homotopy theoretic point of view, the concatenation and inversion are just the first level of a higher groupoid structure. We also need coherence laws on these operations and analogous operations on higher dimensions. For instance, we need to know that concatenation is associative, and that inversion provides inverses with respect to concatenation. So here's a lemma. Suppose A is U, that XYZW of type A, and that P is that X is equal to Y, Q, Y is equal to Z, and R, Z is equal to Y. We have the following. P is P raffle Y, and P is raffle X with P. Okay, sure. I mean, yeah. Why do we need it though? P -1 to P is raffle Y, and P to P -1 is raffle X. Okay, sure. P -1 is P. PQR is PQR. Okay, I mean, sure. Note in particular that these themselves are propositional equalities living in the identity types. All right. So now they like are proving these things. I think this is not that difficult. Maybe it is. I don't know. I think I can skip this. There are other ways to define higher paths. Wait, where is the higher path though? I mean, maybe. Okay, so maybe like the higher path, like we are, yeah, because P is a path, like right. It's the proof that X is equal to Y, and then the equality between proofs means that this is like a higher level path. Yeah, sure. Okay. Types are higher group words. Sure. Oh shit! Look at this. Theorem, Ackman, Hilton, the composition operation of the second loop space. Hold on. Use the omega. What is omega? In this book, we will not need any complicated combinatorics involved in making precise notion of such as coherent structure at all higher levels. In addition to ordinary paths, we will use paths of paths. So elements of type B is equal to Q over the type X is equals to Y over A, which is remarked previously we call two paths or two-dimensional paths, and perhaps occasionally paths of paths. Yes, which we call three paths or three-dimensional paths. It is possible to define a general notion of n-dimensional path, but we will not need it. We will, however, use one particularly important and simple case of higher paths,
which is when the start and end points are the same. In set theory, the proposition A is equal A is entirely uninteresting, but in homotopy theory, paths from a point to itself are called loops and carry lots of interesting higher structure. Thus, given a type A with a point A, we define its loop space as sigma. Okay, so sigma is a loop. Since any two elements of sigma A are paths with the same start and end points, we may write sigma A if the point A is understood from context. Okay. Right. Since they have the same start and end points, they can be concatenated. Thus, we have an operation sigma A times sigma A into sigma A. Yes, more generally, the higher groupoid structure of A gives sigma A the analogous structure of a higher group. It can also be useful to consider the loop space of A. The loop space of loop space, which is the space of two-dimensional loops in the identity loop of A. This is written as sigma squared, as represented as in the type theory as the type Raffle A is Raffle A. While sigma squared omega squared as a loop space is again a higher group. It now also has some additional structure resulting from the fact that its elements are two-dimensional loops between a one-dimensional loop. The theorem: the composition operation of the second loop space sigma omega squared of A times omega squared of A is omega squared of A. Right. So like this is something that we need to prove, right? We know that omega and omega can give us omega by concatenating those. Composition operation. Oh no. We just need to prove that this is commutative. Yeah. Proof. First, observe that the composition of one loops induces an operation star as follows. Consider the elements A, B, C. A and 1, 2 paths. P. A is B. Q. A is B. Alpha. P is Q. R. B is C. S. B is C. Beta is R is S. It is depicted in the following diagram with paths drawn as arrows. So we have like A, B, C, right? We know that A is equal to B in two different ways, P and Q. We know B is equal to C in two different ways, R and S. We know that P and Q, these two paths are equal with alpha and beta. Composing the upper and lower one paths respectively, we get two paths, PR and QS. And there is then a horizontal composition, AB, alpha, beta, PR is QS between them, defined as follows. First we define now suppose that A is B is C, that all the one paths PQR and SL elements of omega AA, and assume moreover that PQRS is Raffle A. They're composable of both order. In that case, we have AB, A star B is the same as A concatenated with B. Recall that this by the computation rule for path induction. On the other hand, we can define another horizontal composition. But in general, the two ways of defining horizontal composition agree. We can see by induction. The foregoing fact, which is known as Ackman-Hilton argument, comes from the classical homotopy theory and indeed is used in chapter 8 below to show that higher homotopy groups of a type are always abelian groups. The Whiskerian and horizontal composition operations defined in the proof are also a general part of the infinite groupoid structure of types. They satisfy their own laws, such as this. Did they forget the R here? Maybe not, because this is, yeah, it's a different operation, yeah. And so on. From now on, we trust the reader to apply path induction whenever needed to define further operations of this sort and verify their properties. In this example, suggests the algebra of higher path types is much more intricate than just the groupoid-like structure at each level. The levels interact and give many further laws. Pointed type is a type AU together with a point A called its base point. A pointed type is a type together with a point called its base point. We write U dot, which is a sigma AUA for the type of pointed types in the universe U. So it's a type together with the base point. Given a pointed type, we define a loop space of this to be the following pointed type. Omega is the same as a so this is a omega is a pointed type where the type is the fact that A is equal to A, and the point is the reflection point. An element of it will be called a loop at A. For n being a natural number, the n-fold iterated loop space of a pointed type is defined recursively as this. The element of it will be called n-loop or n-dimensional loop at A. We will return to iterated loop spaces chapter 6 to 8. Okay, I think this introduction, types are higher groupoids, was difficult. Let's see what the other things are. Functions are functors. This should be easy to understand, right? I think. Now we wish to establish that functions behave functorially on paths. In traditional type theory, this is equivalently the statement that functions respect equality. Topologically, this corresponds to saying that every function is continuous, which means that it preserves paths. Are they not going to say what a functor is? Suppose that f is a function from A to B, then for any x and y, there is an operation. Don't you know category theory? No.
Category theory, by the way, is chapter 9 in this book. So like I'm supposed to know about this in the future. And they're using a concept from the category theory like here in the chapter 2 before chapter 9. Category theory is like one of the last things. So we have a function for any x and y. There is an operation app f, which is a function. If we know that x and y are equal, then we know that application of functions is also equal. All right, this yeah. So basically this means that that applying a function with equal argument gives us equals results. That's what it says. Moreover, for each x, a, we have f reflex is refl f refl fx, sure. The notation AP can be read either as the application of f to a path, application to a path, or as action on paths of f. Sure. Proof. Okay, I don't think I... Oh, wait. This is it? This is it? This is all? Functions are functors? It's like this small? Okay. Sure, let's see the proof. Then... let D be for all x, y into U to be the type family defined by D. XYP is fx equals fy. Right, because that's what we're trying to do. Then we have D. Which is lambda x refl fx. By path induction, we obtain application f for all x, y, if x is equals y, and then this. The computation rule implies app for refl x is refl x for each x a. Second proof, to define app f for all p x is y, it suffices by induction to assume p is refl x. In this case, we may define app f p is the same as refl fx. We will often write app f as simply fp. So we apply a function with the path instead of the actual argument. This is strictly speaking unambiguous, but generally no confusion arises. It matches the common convention in category theory of using the same symbol for the application of a functor to objects and to morphisms. Yeah. We note that AP behaves functorially in all the ways that one might expect. I don't know what to expect though, but sure, it behaves. For functions f, okay, next lemma. For functions f from a to b and a function g, b to c, and paths x is equal to y and q, y is equal to z, we have these four things. So this is for like higher level things. Functor laws are FID is ID and FAB is FAFB. So this is like the second law of functor, right? But why do we try to prove four things here? Because this is only one thing, and then we also define like these other things. This is the rule for functor, right?
proof left to the reader. So we have like the if we apply function to the concatenation of P and Q, it's the same as applying function to P and concatenating that with applying function to Q. App F. If I apply function to the negated path, then it's the same as negated path of applying the function to this path. Wait, no, this is the rule for functor, right? Or something. This is the 3 one. If I apply function G, all right, whatever. As was the case for equalities in lemma 2, those are themselves paths which satisfy their own coherence laws, and so on. Type families are fibrations. All right, do you know what a fibration is, Ertzel? Since dependently typed functions are essential in type theory, we will also need a version of lemma for these. Lemma 221. For these. However, this is not quite so simple to state. Because if a function is for all x, a, bx, so this is a dependent function, and p is the proof that x is equal to y, then fx is having the type bx and fy is having the type by are elements of distinct types, yes. So that a priori we cannot even ask what they are, whether they are equal. The missing ingredient is that P itself gives us a way to relate the types, right? So we need to, like, basically, if x is equal to y, then bx and by is the same type, right? That's what we're trying to do. Relating the types. We have already seen in section 112 where we called it indiscernibility of identicals. We now introduce a different name and notation for it that we will use from now on. Lemma transport. Suppose that P is a type family over A and that P is x equals y. Then there is a function P star from Px into Py. So basically we can have a type Py if we know Px. First proof. Let D be for all x, y, and u be the type family defined by Px into Py. Then we have the function D of the x id Px yes. So that the induction principle gives us that. Yes, alright, this is easy. Second proof, by induction it suffices to assume P is a reflex. But in this case, we can take ref x star type Px into Px to be identity function. Well, I mean, this is second proof. I mean, I understand the first proof, so I don't really need that. Sometimes it is necessary to notate the type family P in which the transport
operation happens. In this case, we may write transport P minus is Px into Py. Recall that a type family P over a type A can be seen as a property of elements of A, which holds at X. If A is in X, if Px is inhabited. Then the transplantation lemma says that P respects equality in the sense that if X is equal to Y, then Px holds if and only if Py holds. In fact, we will see later that if X is equal to Y, then actually Px and Py are equivalent. Logically, the transportation lemma can be viewed as a path lifting operation in a fibration. We think of a type family as a fibration with the base space A. Okay, I guess they don't want to tell us what a fibration is. A fibration generalizes the notion of a fiber bundle and plays an important role in topology. Fibration is a mapping from E to B, satisfying homotopy lifting property for all spaces X. Space B is called base space. Space E is called total space. The fiber over B is the subspace. Let's ignore this thing. Fiber over X, and with sigma X APX being the total space of the fibration. With first projection, the defining property of a fibration is that given a path from X to Y in the base space and a point U and the fiber over X, we may lift the path P to a path in the total space starting at U. And as lifting can be done continuously. The point P star U can be thought of as the other endpoint of this lifted path. Okay, sure. I think I understand. Maybe path lifting property. Let P be A into U to be a type family over A, and assume we have U Px for some X of A. Then for any P X is Y, we have lift UP XU. So this brackets is like the pointed type. No, what was it? I think that was the pointed type type together with the base point. But if is X a type? It's something. XU is the same as Y B star U. Yeah. So this is yeah. Yes. I get it. I will not explain anything to you though. I will just pretend that I understand it. Lifting a path. Proof left to the reader. We will prove a more general theorem in 2.7. In classical homotopy theory, a fibration is defined as a map for which there exists liftings of paths, while in contrast, we have just shown that in type theory, every type family comes with a specified path lifting function. Every type family comes with a specified path lifting function. This accords with the philosophy of the constructive mathematics, according to which we cannot show that something exists except by exhibiting it. It also ensures automatically that the path lifting are chosen continuously, since, as we have seen, all functions in type theory are continuous. Remark. Although we may think of type family P from A to U as like a fibration, it is generally not a good idea to say thing like the fibration P, since this sounds like we're talking about a fibration with base U and a total space A. To repeat, when a type family P is regarded as a fibration, the base is A and a total space is this. We may also occasionally use other topological terminology when speaking about type families. For instance, we may refer to a dependent function as a section of a fibration. And we may say that something happens fiber-wise if it happens for each px. For instance, a section f for all x of a px shows that p is fiber-wise inhabited. A mapping E to B satisfies the homotopy lifting property for space X if for every homotopy H and for every mapping H0 X to Y lifting H is H0. H0 is P. P is this mapping. The following commutative diagram shows the situation. All directed paths in the diagram with the same start and end points lead to the same results. It is said that commutative diagram plays the role in category. Oh, this is too difficult. Oh, we can prove the dependent version of lemma. The topological intuition is that given f for all p, for all x, px, and a path where x is equal to y, we ought to be able to apply f to the path and obtain a path in the total space of P, which lies over P as shown below. Okay, so the total space is if x is a, px. Yes. Yeah, actually this is understandable. Yes. So like we want to prove that the result of the of applying a dependent function is the same if the argument is the same, right? But the problem is that like if we know that the arguments are equal, right? So the arguments are equal, but the result of a dependent function, the type of the results depends on the actual value of the argument, right? So in order to define the type representing all possible outcomes of the function that is dependent, it is a dependent pair, right? So in order, so like the type of the result is kind of the depends on the type of the argument. So we store this inside of the type itself, right? So this is like the total type of the result of the function f, right? So sigma means that it exists, right? So when I apply a function, dependent function, with x being the argument, the resulting type is dependent on this argument. Yes, this makes sense. So that's why we represent the equality of the result in this type, because we can only represent equalities when the type is the same thing. Yep, okay. I understand this. The idea, I think. We can obtain such a thing from lemma. The solution is to use transport lemma. We have a canonical path lift. Alright, lemma 234, dependent map. Suppose f is a dependent function from x to px. Then we have a map, d, which is for all proofs that x is equal y, p star fx is equal to fy. Yeah. P star fx is equal over py. So like this is oh, because this is p star, yeah. So like yeah, because the type of fx is px, not py, right? Sure. A lemma if p. The other lemma, if p is a function from a to u is defined by px is b for a fixed b, then for any x and y and p, which is x is equal to y, and b of type b, we have a path. Transport const e over b. B is transport pb is b. Sure. Lemma 238 for f a into b and p x equals y, we have empty f P is transport const. Transport const, yeah, fx. Number 239, given P from A to U with P x is equal to y and Q y equals z, while U Px, we have Q star P star U is PQ star U. For a function f a to b and a type family p bu and any p x is y and u p of x, we have transport p and f for pq au and a family of functions and any of this. All right, just going to skip through some of that. Homotopies and equivalences. So far we have seen how the identity type can be regarded as a type of identifications, paths or equivalences between two elements x and y of a type A. Now we investigate the appropriate notions of identification or sameness between functions and between types. We'll see that homotopy type theory allows us to identify these with instances of the identity type, but before we can do that, we need to understand them in their own right. Traditionally, we regard two functions as the same if they take equal values of all inputs. Under the propositions as types interpretation, this suggests that two functions f and g, perhaps dependently typed, should be the same if the type role x fx is equal to gx is inhabited. Yes, this makes sense. So this is how we define that two functions are same. Yes, if we have this function is inhabited. Under the homotopical interpretation, this dependent function consists of continuous paths or functional equivalences, and thus may be regarded as the type of homotopies or of natural isomorphisms. This we will adopt the topological terminology for this. The dependent function type consists of continuous paths. And thus may be regarded as the type of homotopies. Okay. Let fg be a dependent function with two sections of a type family. A into u. A homotopy from f to g is a dependent function of type this. So like that's what we were saying here. Yes. So f is equivalent to g means that this is inhabited. Know that a homotopy is not the same as identification. However, in 2.9 we will introduce the axiom making homotopies and identifications equivalent. Okay. Homotopy is an equivalence relation for each dependent function type. That is, we have elements of the type role f, which is a dependent function. F is the same as f. Okay. For all f and g, which are both dependent functions, if f is equivalent to g, then g is equivalent to f. Right? And then it's transitive too. Okay, sure. Just as functional type theory are automatically functors, homotopies are automatically natural transformations. Sure. Lemma 2 for 3. Suppose hf is equivalent to g is a homotopy between functions f and g. And let p x is equal to y. Then we have hold on, h is a homotopy. Homotopy means that hx is a proof basically that fx is equal to gx. Yes. So this is fx equals to gx. And then we have also gp. gp is applying the g to the path. So the result is not b. But it's a path from b to b. So this is a path. I mean, this is a path from b to b too. Yeah. All right. Sure. We can concatenate those. This is the same as fp with hy. We may also draw this as a commutative diagram. Fx, Fy, Gx, Gy. So those are equal to each other. No, Fx is equal to Fy because of P. Because x is equal to y. Yes. All right, sure. Corollary. Wait, what is this word even meaning? A proposition that follows from an already proved one. Let H homotopy FIDA then for any x of A we have H fx is fhx. Definition for a function AB, a quasi-inverse of f is a triple GA alpha beta consisting of a function and a homotopies. Higher groupoid structure of type formers. Alright, I think we're getting into the point where I am starting to understand nothing. So, in chapter 1, we introduced many ways to form new types, Cartesian projects, disjoint unions. Does that mean we're making progress? We're making progress towards rage quitting and working on useful things instead of doing the stupid math. Who needs math anyways, right? Turns out that for many types A, the equality types actually are going to be characterized up to equivalence. the equality types can be characterized up to equivalence in terms of whatever data was used to construct A. For example, if A is a Cartesian product BC and X is BC and Y is BC, then we have equivalence like that. In more traditional language, two ordered pairs are equal just when their components are equal. The higher structure of identity types can be expressed in the terms of these equivalences. Let's just skip through Cartesian product types. Given types A and B, consider the considered product type A times B. For the elements X and Y of the product and the path X is equal to Y. By functorially, we can extract the paths that the first element we can extract paths PR1 P which is PR1X is equal to PR1Y. Okay. And PR2 is equal to PR2. Sure. Thus we have a function. So basically this says that if we know that two product types are equal, then we know that their first elements are equal and their second elements are equal. For any X and Y, the function this function is an equivalence. I don't know what an equivalence is even. But logically, this says that two pairs are equal if they are equal component-wise. Read category theoretically. This says that the morphism is in a product group where there are pairs of morphisms. With homotopical theoretically, this says that the paths in a product space are a pair of paths. Yes. Sure. Do I need the proof? I don't know. Theorem, the next theorem. In the above situation, we have transport AB X is sigma types. Dependent pair type is generalization of the product type. Thus, we expect the higher group would also be a generalization of the previous section. Its paths should be pairs of paths, but it takes a little thought. Give the correct types of these paths. So, like similarly to the dependent function, the path on the second argument is the path in the total space or something. A fiber, of course, yes. We have fibrations here. This is understandable. Let's skip through. The unit type. Trivial cases are sometimes important. So we mentioned briefly in the case of unit type 1. For any X and Y, which is a unit, we have X is equal to Y is equivalent to unit. Maybe tempting to begin this proof by one induction on X and Y and reducing the problem to this is 1. However, at this point we should be stuck since we would be unable to perform a path induction on P. Thus, we instead work with the general X and Y as much as possible, reducing them to star by induction only at the last moment. P-types and function extensionality axiom. Given a type A and a type family B, consider the dependent function type. We expect the type
f is g of paths from f to g to be equivalent to the type of pointwise paths given a type A and a type family B. Consider the dependent function type for all x, a, b, x. We expect the type f is g of paths from f to g in this to be equivalent to the type of pointwise paths. So is if f is equal to g, it's equivalent to fx is equal to gx. From a traditional perspective, this would say that two functions which are equal at each point are equal as functions. From a topological perspective, it would say that a path and a function space is the same as continuous homotopy. Axiom, function extensionality. For any a, b, f, and g, the function is an equivalence. This function is an equivalence. H apply. Oh, so this is like just getting. If we have the proof that f and g are equal, then we also have this thing. Sure. And this function is an equivalence. Given time families, we have equivalence. Universes and the univalence axiom. Given two types A and B, we may consider them as elements of some universe type U, and thereby form the identity type A is B. As mentioned in the introduction, univalence is the identification with the type of equivalences from A to B, which we described in 2.4. We perform this identification by the way of the following canonical function. ID to equivalence. If A is equal to B, then A is equivalent to B. Where was the equivalence introduced, though? What is an equivalence? Okay, and the equivalence from A to B is defined to be a function from A to B together with an inhabitant of is equiv f. So there exists a function where is equiv f. And what is equiv? Is equiv f is this thing. There exists a function from B to A. And so for each arm function, there's a function inversed function. There's a function q into is equiv. Right, is equivalent f is So there exists a function from B to A, so like the inversed function, such that f and g together is IDB. And there's also exists another function from B to A, which we combine in the other, and we have like the A back. So this, what does this mean? Is equiv f. F is equivalent. This means that we can like does this mean that just the inverse function exists? Kind of. And so A is equivalent to B if we have a function which is like this function. Like an inversible function. Why is it called equiv? And though like they have the qinf, whatever that is. Where's qinf in? Moving on to types. Oh, okay, there we go. A homotopical perspective suggests that this should be called homotopic equivalence, and a form of categorical one should be called equivalence of higher group weights. However, when to prove relevant mathematics, the corresponding type is poorly behaved. Where's qinf? Quasi-inverses of f. 2, 4, 5. This is a quasi-inverse. So how is it different? This says that there exists a function g from B to A where fg is B and gf is IDA. So like the difference between this inversion and the other inversion is that like we have two different functions in the equiv, and over here we have only one function. Why is it poorly behaved? For instance, if for a single function f from A to B, there may be multiple unequal inhabitants of this. For a single function, there will be multiple unequal inhabitants. This is closely related to the observation in higher category theory that often needs to consider adjoint equivalences rather than plain equivalences. For this reason, the following we give this the following historically accurate but slightly derogatory sounding name instead. Yo, big early, hello. There may be multiple unequal inhabitants. Cannot the same be said about this function though? So we will reserve the word equivalence for an improved notion of is equiv with the following properties. For each f a to b, there is a function q into is equiv. I mean, we can get the is equiv there. All right, sure. Similarly, for each f, we have is equiv to qinf. Thus, the two are logically equivalent. For any two inhabitants, e1, e2 is equiv. We have for any two inhabitants, we have e1 is e2. So like basically
All of the possible definitions, all of the possible inhabitants are equal to each other. And that's not true about these ones, right? So property 3 is not hard to prove, but requires identifying the identity types for Cartesian product and the pair types. Alright, whatever. For any A, B, U, the function is an equivalence. ID to equiv. If we have a ID, then A is equal, is equivalent. Alright. The axiom univalence for any ABU, the function is an equivalency. But particular, therefore, we have AB is equivalent to A being equivalent to B. Technically, the univalence axiom is a statement about particular universe type U. If a universe satisfies this axiom, then we say that it is univalent. Except when otherwise noted. We will assume that all universes are univalent. We mark. It is important for the univalence axiom that we defined the equivalence using a good version of isEquiv, rather than say that there exists a QInf. Yes. Just looking at that. In particular, a univalence means that equivalent types may be identified. As we did in previous sections, this is useful to break the equivalence into an introduction rule for equality, denoted UA for a univalence axiom. So now it's the other way around. If we have equivalence, then we have equality. Identified means being equal. Right? The elimination rule, ID to env, ID to equiv. The propositional computation rule, the propositional uniqueness principle. We also identify reflexivity concatenation versus brain type family. B A to U and XAA with a path X equals Y and UBX. We have transport PU is transport. Identity type, just at the type, ID is IDA. It's characterized after isomorphisms with a separate definition for each A. There is no simple characterization of the type. Skew of paths between paths. However, our other general classes of theorems do extend to identity types, such as the fact that they respect equivalence. If a function is an equivalence, then for all A and A, so is this. So this is also an equivalence. The equality is the same as that. Proof. For any A and A, B, we have that. Co-products. Far most of the type formers we have considered have been what are called negative. Intuitively, this means that the elements are determined by the behavior Under the elimination rules, a dependent pair is determined by its projections, and a dependent function is determined by its values. The identity types of negative types can almost always be characterized straightforwardly, along with all their higher structure as we have done. The universe is not exactly the negative type, but its identity type behaves similarly. Now consider our first example of positive type former. Informally, a positive type is one which is presented by certain constructors with the universal property of presentation being expressed by elimination rule. Categorically speaking, the positive type has a mapping out universal property, while negative type has a mapping in universal property. Because computing with presentations is in general an uncomputable problem, for positive types we cannot always expect straightforward characterization of the identity type. However, in many particular cases, a characterization of partial characterization does exist and can be obtained by a general method that we introduced in this example. Technically, our chosen presentation of Cartesian products and sigma types is also positive. However, because these types also admit the negative presentation, identity types have a direct characterization that does not require the method to be described here. Consider the coproduct type is presented by the injections. Intuitively, we expect that A plus B contains exact copies of A and B disjointly, so that we should have this. And inal A in RB is 0. Sure, we prove this as follows. But isn't this also only true if A and B are different? We prove this as follows. Fix. Oh, I mean, yeah, the constructors are never, even if they are the same. Yeah, whatever. We prove this as follows. Fix an element which will characterize the type family. Whatever. Theorem for all x of A plus B, we have in L A0x is equal x is equivalent to code x. Wait, what is code? Code. In order to characterize, we'll define a type family, code. Code is a type family from A plus B into U, and show that for all x of A plus B, this is equal. That's the theorem that's following. Since we want to conclude from this, we should have code. What is A0? We are trying to prove this, right? We're fixing the element A0 from A. So code in L A is whether A0 is equal to A. So we should have code in RB is 0. The essential insight is that we can use the recursion principle to define code by these two equations. Code in LA is A0 is this, code in RB is just 0. This is a very simple example of a proof technique. So for all x, A plus B, we have NL A0 is the equivalent to code x. Okay, sure. Stand this. I think Natural numbers. We use the encode-decode method to characterize. Hold on, there is encodes, decodes. And the key to the following proof is that we do it for all points x together, enabling us to use the elimination principle on the coproduct. We first define a function in code, which is for all x, and for all p is code x. And then next we define a function decode, which is for all x. And if we have the code x, then we have the x is equal to NL A0. Sure. Using code-decode method to characterize the path space of the natural numbers, which is also are a positive type. So code is basically whether the two things are equal. In this case, natural numbers. So n equals n is equivalent to the code. Sure. Examples: equality of structures. Computer 1 illustrate the interaction between groupoid structure on type and the type formers. So you have groupoids, universal properties. By combining the path computation rules described, we can show the various path forming satisfy things. Sets and logic. Well, the chapter 2 has been seen. Has the chapter 2 been understood? No. I don't think so. The introduction is easy to understand, but then I understand nothing. And what is this useful for? I also don't understand. What else do we have in this book? Do I need to read further? Sets and logic. Type theory is a collection of rules manipulating types and their elements. When writing mathematicals informally in natural language, we generally use familiar words. Particularly logical connectiveness such as and or, and logical quantifiers such as for all and there exists. In contrast to set theory, type theory offers us more than one way to regard these English phrases as operational types. Particular ambiguity needs to be resolved by setting out local or global conventions, by introducing new annotations to informal mathematics, or both. Equivalences. We now study in more detail the notion of equivalence of types. We will give several different ways to define a type is equiv f, having the properties mentioned here. By invertible maps. Induction. In chapter 1, we introduced many ways to form new types from old ones. Except for dependent function types and universes, all these rules are special cases of the general notion of inductive definition. Study inductive definitions more generally. Inductive type can be intuitively understood as a type really generated by a certain finite collection of constructors, each of which is a function with codomain X. Codomain means result type. This includes functions of zero arguments, which are simply elements of X. When describing a particular inductive type, we list the constructors with bullets. 0, 2, 1, 2. The type 2 is a Boolean type. Similarly, 1 is inductively generated by the constructor this, while 0 is inductively being generated by no constructor at all. Okay, sure. Usually we also allow constructors of, hold on. In L is this constructor, in R is this constructor, okay. And as an example, with constructor taking multiple arguments, is the Cartesian product. AB into A with B. Crucially, we also allow constructor on inductive types to take arguments from the inductive type being defined. For instance, the type n of natural numbers has constructor n and suck. Constructors of inductive type to add arguments of the type being defined. Yes. That's why it's an inductive type, right? And like list is the same thing. Okay. Intuitively, we should understand as freely generated by constructors. Rather than assert properties such as this directly, however, wait, what properties? Elements of an inductive type are exactly what can be obtained by starting from nothing and applying the constructors repeatedly. For instance, in the case of 2, we should expect that the only elements of 0, 2, the only elements are 0, 2, and 1, 2. Similarly, in the case of n, we should expect that every element is either a 0 or obtained. Yes. Rather than assert properties such as this directly, however, we express them by means of the induction principle, also called a dependent elimination rule. We have seen this principle already in chapter 1. For instance, the induction principle for 2 is when proving a statement, E 2 into U about all inhabitants of 2, it suffices to prove it for 0 and for 1. Furthermore, the resulting proofs into 2. Lunix uses Hyperland. Yes, I am using Hyperland. Also using NixOS, by the way. This principle is described by the computation rule. Why use Linux though? What should I use instead?
Unless ThinkPad? No. Why use anything but Linux? Why don't you use Windows and make life easier? Why do you think that life with Windows is easier? That's not true. The only difference is the amount of learning, I guess, that you need to do. Use Windows, you don't need to learn much. It's something that can be used by a monkey, right? But if you're capable of learning and you learn a little bit, then Linux is actually easier than Windows. Resulting proof behaves as expected when applied to constructor 01. This principle is expressed by the computation rules. Thus, the induction principle of Booleans allows us to reason by case analysis. Since neither of the two constructors takes any arguments, this is all we need for Booleans. For natural numbers, however, the case analysis is generally not sufficient. In the case of corresponding to the inductive step suc n, we also want to presume that the statement being proven has already been shown for n. This gives us the following induction principle. Almost all programs are designed to be made from Windows, and Windows is simpler. So I bother with Linux. I used Arch, by the way, on my second PC, but I see no use for it on a capable PC. Almost all programs work on Windows and Linux. Most of the things that work on Windows work on Linux. I'm playing games that work only on Windows, and I'm playing them on Linux. I don't need Windows to play my games. It's mostly about games, I think, usually. Anything that you need to work. Like, I'm a programmer, right? So in order to do the programming, it's it's actually like a lot easier to like install a compiler on Linux than it is on Windows, because like of the package managers, right? Like, you've used Arch, you just do pacman-s GCC and you have a GCC on your PC. If you have a Windows, you need to like go to the website, download, extract it somewhere, put it into your path so that you can use it, and then like when you want to upgrade it, when you want to update it, you're going to hate your life. Nope. Nope, what? This is just for you, but professional programs struggle to work on Linux, and gaming on Linux sucks simply because NVIDIA doesn't have proper drivers, which is what the majority of people use. I don't know, I can game on Linux, it's not a problem. I mean, not everything works on Linux, sure. Not everything works on Linux. Not everything works on Windows. There are some programs that are that are just working on Linux too. You can't argue with what? Professional programs struggle to work on Linux. What is a professional program? Like, again, I'm a programmer. The professional program that I use is like, I don't know, VS Code, Vim, I don't know, like whatever else, I don't know, Sublime Text, IntelliJ IDEA, right? What else? All of those work on Linux. Those are professional programs. They don't struggle. If you say about like, I don't know, like, it depends on the profession, I guess. Maybe like some audio programs, some digital audio workstations, they don't work well on Linux. Maybe, I don't know. I didn't try, because that's not what I'm doing.
And as in the case of the booleans, we also have the associated computation rules for the function. The dependent function int n can thus be understood as being defined recursively on the argument x n, where the functions ez and es, which we call the recurrences. When x is 0, the function simply returns ez. When x is the successor of another natural number, the result is obtained by taking the recurrence es, substituting the specific predecessor n and the recursive call. The induction principle for all examples mentioned above share this family resemblance. We will discuss a general notion of induction definition and how to derive an appropriate induction principle for it. But first, we investigate various commonalities between inductive definitions. For instance, we have remarked in every case in chapter 1 that from the induction principle we can derive the recursion principle, in which the codomain is a simple type rather than a family. Both induction and recursion principle may seem odd, since they yield only the existence of a function without seeming to characterize it uniquely. However, in fact, the induction principle is strong enough to also prove its own uniqueness principle. As in the following theorem, let f and g be for all x, ex. What's e? What is e? It's something. Be two functions which satisfy the recurrences. Ez is e0. Oh, this is just like for natural numbers. So ez is e0 and es for all natural numbers, en into e sec n. Up to propositional equality such that f0 is ez and g0 is ez, as well as and f and g are equal. Sure. Now that the uniqueness principle applies even to functions that only satisfy recurrences up to propositional equality. Path. Of course, the particular function obtained from the induction principles satisfies these recurrences judgmentally. We have defined the natural numbers to be particular type n with a particular inductive generators 0 and suck. However, by the general principle of inductive definitions in type theory, there is nothing preventing us from defining another type in an identical way. That is, suppose we let n quote be the inductive type generated by the constructor this. Then this will have identically looking induction and recursion principle. When proving a statement for all the new natural numbers, it suffices to give proofs, and the function has the following rules. But what is the relation between n and n? This is not just an academic question, since structures that look like natural numbers can be found in many other places. For instance, we may identify natural numbers with lists over the type with one element. This is arguably the oldest appearance found in walls and caves. With the non-negative integers. What do you mean non-negative integers? Isn't natural number the non-negative integer in this case, because we have zeros? The subsets of the irrationals, the reals, and so on. And from a programming point of view, the unary representation of our natural numbers is very inefficient, so we might prefer sometimes to use a binary one instead. We would like to be able to identify all of these versions of the natural numbers with each other in order to transfer constructors and results from one to another. Of course, these two versions of the natural numbers satisfy identical induction principle, then they have identical induced structure. For instance, recall the example of the function double. The similar function for our new natural numbers is readily defined by duplicating and adding primes. Simply as this may seem, it has the obvious drawback of leading to a proliferation of duplicates. Jamie Collis. Good day, hello. Not only functions have to be duplicated, but also all lemmas and their proofs. In traditional mathematics, one just proclaims that n and n are obviously the same. Adobe stuff, some Unreal Engine stuff, art programs, also games can run because of anti-cheat, which is what the majority of people play. Since cheat games like Fortnite, etc., Steam needs to compile shaders before launching a game, otherwise it lags. Nvidia is superior on Windows, and most of the performance increase and AMD offers on Linux doesn't do much difference because Adrenaline control panel isn't there available to use stuff like AFMF. Most stable Linux don't release driver fixes for new GPUs or hardware, so you have to be on a rolling release which is prone to breakage. Well, this is why you use NixOS, because you can always roll back easily. Like, that's why it's better than Arch Linux. Because in Arch Linux, if you upgrade and if something breaks, going back in time needs like... I mean, it's possible to like have other solutions, but in Nix it's just so easy to roll back if something breaks. Is this book available online for free? Yeah, it is. Just search for hot book. It's over here. Most people don't want to deal with all that. Windows makes it easier. No. I guess. Yeah. Like, I mean, what are you trying to say? Like, I'm not most people. I'm using the programs that I use. For example, I don't do Unreal Engine. I don't do art program. I don't do games with anti-cheat. So, like, why do I care that those things require Windows? I don't fucking care, right? For my for the way I'm using my PC, Linux is strictly better. I don't care what's better for most people. Right? I'm trying to make my life easier. Go Linux. I have plans to build more more secure OS starting from open source options. Nice. I'm not as far yet as to building my own operating system. So far, all the things that I have is I have a custom game engine, and I'm working on my programming language, which is why I'm reading this book to give me some ideas. But my own operating system, maybe my own custom like text editor, which is better than Vim and VS Code and like Helix and all of those options. They all suck, right? So we need something better. Maybe. I'm not ready for it yet, though. Eventually, maybe. A more secure operating system. Yeah. The goal is like a full-on Iron Man lab. Yeah. What's even is NixOS? You can search it up. NixOS is over here. No, this is unofficial. NixOS. NixOS is a Linux distribution, but it's like declarative. So
Like you've used Arch. So when in Arch Linux, you just say install this thing, and then you forget about it. And if you go to a new PC and you want to have the exact same system, then you need to remember what you have done, or you need to like, or you need to duplicate the work when you're installing your software to like put it into the like into a version control, but also like you don't really like test the fact that your like way to reproduce your current system actually works. So NixOS makes it easier. What's it based on? It's its own system. It's not based on any other distro. It's its own thing. So in NixOS, I mean it's based, I guess, on the Nix programming language. They have their own programming language. So here's my operating system, for example, right? Here's how I define my my file systems, for example, right? I mount this to, right? And this is just stored in my Git, and I always know what is the Git revision that I have currently deployed on this PC, and if I want, I can like go back to the old version. Here is how I like install the packages, right? I just list them here, and if something is listed here, then I have it on my then I have it installed. If I don't have it listed here, then it is going to be uninstalled automatically. It's like like your operating system declared in code. Everything you have declared is what you have, instead of it being an imperative thing like most of the other distributions. NixOS is like the only one. There is also GUIX, I guess, which is doing the same thing. I'm not sure. GUIX OS, is there such a thing? Yeah, there is also GUIX. I never tried it, but I think those are the only two that do the things declaratively. You've hearing a lot about Cache OS. Control to replace Nix with Cast. I just got here. Welcome, Spike. Cache OS. Blazingly fast OS based on Arch Linux. Blazingly fast and customizable. Designed to deliver lightning fast speed and stability, ensuring a smooth and enjoyable. If you're a seasoned Linux, or Cache is the ideal choice. What's the benefits? How is it better than Arch Linux? Like, this is based on Arch Linux, so what is different? Enhance your performance with optimized packages. It compiles packages with a v3, v4, and Zen 4 instruction set and LTO to provide higher performance. So like it doesn't work if your CPU is like old, I guess, right? So this one only works on newer hardware. Is that why? And that's why it's faster? Sure. Does this matter that much though? Actually, power up your computer with robust kernel support. Cache OS just an Arch with custom scheduler. What's a scheduler? A scheduler, what, is like a part of the kernel. So it's not even a part of the operating system. It's just a part of the kernel. No, the Bohr scheduler. I don't know. I don't know how kernel works exactly. What is the Bohr scheduler? Burst-oriented response enhancer CPU scheduler. Burst granularity. Burst penalty scale. Is enhanced versions of CFS. Completely fair scheduler. Linux schedulers. So like, can you have like a scheduler swapped out from like whatever is installed in Linux? Is that how it works? I don't know. I don't know. I don't know Linux that well. How it all works. It does make a difference. They try to emulate Mac OS scheduling to ensure a seamless interactive experience. Okay. How does it make a difference though? Like, do I have a problem that needs to be fixed? Boar scheduler NixOS. Can I just do this in NixOS? Linux boar. Is that what I do? Did I just install Linux boar? This is a request though, so it's not there really, right? A set of patches for Linux kernel to add a new scheduler that optimizes for a specific metric. So there is an issue and it's not done. So like eventually we will have it. Someone will do it for sure. Maybe you will do it, Spike, and do a pull request into the Nix packages. Or it's not there. It says open. It's already done. There's a flag that can construct a kernel packages attribute for you to use. It's already done. Yeah, but like this puts it directly into the Nix packages, like pre-packaged Linux board, right? I mean, I can compile my own kernel, right? And it's also done in somebody's flake. I mean, the only thing that I have done is I think I'm using like the Zen kernel. I don't know. I don't really notice the difference though. I think like I'm using the Zen kernel, but I don't think I noticed any difference. And what am I supposed to notice? I have no idea. You don't like using custom kernels? Well, I mean, a custom kernel means that you need to compile it, right? Probably. Instead of just downloading it from the cache. Which means that updating will take more time. Where did the thing on the left go? Ah. Oh, there you go. Oh, I see. Can I pin this? No? Alright, sure. Make host, args, host platform, lib system, architectures, feature suppose event 4. Like, is this from an extra module? Like this feature, lib systems, architecture support, host platform. Is that... Like, what even is this? Is this part of the Nix packages, modules, make host, libbird? Is this your own library? Lib. Default. Bird. My god. How to, like, navigate the Nix source code? I have never learned this properly. Where is bird? There is bird OS. That's not bird. Lib bird. What is a lib? You only like Arch because you can literally shape it into anything as long as possible. Well, that's why NixOS is better. You can also shape it into anything. I don't know, like there was a person some time ago who was going to do Linux from scratch with Nix. I don't know if they did it. A Linux from scratch with Nix. Nix LFS. There you go. Linux from scratch with Nix. You can do anything. Like Nix is not just an operating system, it's a programming language, a package manager. At this point, Linux is a huge-ass cult. Sure, yes, I guess. I mean, everything is a cult. Apple has their own cult. I don't know if people who use Windows can be called a cult, though. But I guess Linux users can be called a cult, and Apple users also. You don't think Windows does? I don't know. What about like iPhone versus Android? Are those two both cults? Think so. Apple cult doesn't know why they are a cult. And if they do, their reasons are bad. Well, whether you know that you are a cultist or not doesn't mean that you are not a cultist, right? All right, what are we doing? So, like, Spike, you just joined the stream recently. Yesterday, I think like this chapter type theory of the book is like relatively understandable. It's easy. The most useful thing that I got from this book is like this idea of propositions as types. But the homotopy type theory that I was reading through today, I don't know. I don't know. I don't know about this one and what is it useful for me as a like language maker. I understand some of the ideas, but like what are they useful for? I have no idea. It's just math with no purpose so far. I'm just not seeing it. I mean, having strong enough math foundations really helps. Yeah, sure, but like I mean I understand what like the analogy, right? The that these are paths, like whatever, like the infinite groupoid, I even understand that, but like what is it useful for? Have you read this book? Do you know what this is all about? I like my goal is to make a programming language, right? So reading through the type theory, like dependent functions, dependent pair types. I knew this before reading this book, but like technically this is really useful. Dependent functions, dependent pair types, really good. Propositions as types is useful. Nothing from the homotopy type theory so far is something that I can apply. You're interested in reading it in the future? Yo, Ogma, hello. You got a haircut? Yeah. You like it? You didn't know it exists until my stream of this book? Yeah, I only learned about this recently too. There's also like the category theory. So I have heard about category theory. But I don't know. Is Nerdsel still here? Nerdsel, what is category theory useful for? Is it useful for something? Or is this just math? Useful? Why? I don't know. Like you know category theory, right? So have you used it to make like during game development? Have you used it for something? A little bit? Data analysis? What is this? Mm, mm. The Yonah dilemma. For a pre-category A, its opposite A-op is a pre-category with the same type of objects with home A-op. AB is home ABA. Nice. It's related to type theory, so kinda not really though. Reasoning about the universe and human behavior. Mm, mm, mm. What's higher inductive types?
Accept the general schema for defining new types generated by some constructor, but unlike ordinary inductive types, define higher inductive types. We may have constructors which generate not only points on that type, but also paths and higher paths in that type. For instance, we can consider the higher inductive type S1 generated by a point base of type S1 and a path loop base XS1 base. This should be regarded as entirely analogous to the definitions of, for instance, 2. 2 is a Boolean, as being generated by a point 0 and a point 1. Wait, well, how is this analogous? A point and a loop? We may have constructors which generate not only points, but also paths. Anal, a gas?
Analogous. Analogous.
No, it's analogous. That's literally how I said it.
Analogous.
That's how I said it, right? It's not analogous. It's analogous. I said just? Analogous? Did I say that? All right. Higher constructors. Okay, hold on. How is this analogous? A point and a path loop. This has been entirely analogous to 2 or the definition of n. What? I mean, the 2 and n is definitely not analogous, right? This is a natural number, this is a Boolean. When we think of types as higher groupoids, the more general notion of generation is very natural. Since a higher groupoid is a multi-sorted object with paths and higher paths as well as points, we should allow generators in all dimensions. Oh, okay. All right. Okay. Yo, wait, hold on. Nerdsel, you tried lean 4, right? Lean 4. I thought they called something like inductive types too, right? Do they have higher inductive types? Whatever that is, documentation. Search tree examples. Link language reference. So they have... Can I jump to inductive types? No, they have just inductive types, right? Or do they have higher inductive types? Inductive types are the primary means of introducing new types to Lean, while universes, functions, and quotient types are built-in primitives. Every other type is either an inductive type. Yeah. So constructors and their constructors. Inductive type declaration. Inductive. Declaring inductive type is type constructor, constructors, and recursor are present in the environment. New inductive types extend the in-score logic. They are not encoded or presented by some already present data. First means of declaration from inductive or where. Parameters and indices. Example, constructorless type. So yeah, sure. Constructorless proposition. No. Okay, so actually, so they have the types and propositions as different universes, actually, just like I was suggesting. I think Lean 4 is a good language to look at. For this, did you write any
proofs in Lean when you were trying this? No? Proposition, a type with parameter and an index. Anonymous constructors. Constructors can be invoked anonymously by enclosing their explicit arguments in angle brackets, separated by commas. Anonymous constructor. Inductive at least one. Make. A. Option at least one A. Anonymous constructor syntax can be used to construct them. Oh, you can like call anonymous constructor syntax. Okay. Anonymous constructor. If it says just one constructor, yeah, okay, sure. It's just a syntax for inferring the constructor name, I guess. Field structure, constructors. Logical model. Any reductive type is equipped with a recursor. So, for example, when I was reading this book, we not only have recursors, right? We also have like whatever, like the induction principle. There's a recursion, but there is also induction. But they only have recursors. Recursor takes the following parameters: the inductive types parameter, the motive. The motive determines the type of the application. These are functions whose arguments are type indices and an instance of the type. Major parameters for target. Example: a recursor for bool. The return type is the motive bool into sort U. A specific universe in Lean's infinite hierarchy of universes. A sort universe. Motive false, motive true. The recursor for list. Alright, so higher inductive types, they allow us to specify paths. In addition to just points. The interval, which we denote I, is perhaps an even simpler high inductive type than the circle. It is generated by a point 0, point 1. Okay, so yeah, basically, so we can have a, yeah, so higher inductive type allows us to specify an interval, which is 2 points plus the path between them. The regression principle for the interval says that given a type B, interval, interval, a point B0, the regression principle for the interval says that given type B along with a point, like 2 points and a path, there is a function from the interval into B. Yeah, sure. Type I is contractible. Proof. What is contractible? No idea. Circles and spheres. We have already discussed this circle S1 as the higher inductive type generated by a point and a path loop. So that's what a circle is, yeah. It's a point plus the loop that goes through this point. His induction principle says that given P and L, its non-dependent recursion principle says this. We observe that the circle is non-trivial. Loop is not raffle base. Yeah. Sure. Is the type S1 belongs to some universe U, then U is not a one type? Suspensions. A suspension of a type A is a universal way of making the points of A into paths. And the paths in A into two paths and so on is a type sigma A defined by the following generators. A point N, point S, and a function which takes A and returns an S. Why is this as an argument though? I mean, yeah, I guess. A universal way of making the points into paths. So this means that there is only one path in this type from 2 points. Names are intended to suggest the globe of sorts, a north pole and a south pole. And this is a meridian. What's this useful for? Cell complexes. In classical topology, a cell complex is a space obtained by successfully attaching disks along their boundaries. A cell complex is a space obtained by successively attaching disks along their boundaries. It's called a CW complex, clockwise complex, if the boundary is constrained to lie the disk strictly less than n, the n-1 skeleton. A disk's made out of hub and spokes. Hubless spokes. Hubless spokes 2. Push outs. I only know what a push up is. It's a push out. Audience. A particularly important sort of colimit of sets is the quotient by relation. That is, let A be a set and R be AA prop, a family of middle propositions, a relation. Its quotients should be the set co-equalizer of the two projections. Algebra. A monoid is a set. All right. I think we can be done with this book. Maybe I will at some point come back to it to learn more. I've learned enough for now. What do I do next time? I was going to actually like I remember I was doing the subtyping research before the hot book. I think instead of subtyping, I'm going to remove that. In fact, I already did remove it. The new algorithm with subtyping, and instead we're going to try to do the row polymorphism. Which is allows to achieve similar things, I guess. So the idea is kind of something like this. If we are doing the subtypes, then we say like A is a subtype of B, right? So it's like less than or equal than B. So instead of saying something like this, we can say that A plus some C is equal to B, right? So we don't have the inequalities anymore. We only have like this thing. And I think in this case, for row polymorphism to work, one of these things, like only one of these things in addition, can be the unknown variable. So one of these is a constant, and then we have the addition to some unknown variable. And that's how I can summarize the row polymorphism, I think. I'm not sure though. But we can use row polymorphism to do the effect system and to do the different like normal row polymorphism stuff with the records. So if I want to write a function that does something with x and y, I want to accept any structure that has x and y, then we do this. The row polymorphic record types allow us to write programs that operate only on a section of a record. Is my mic cutting out? I don't know, maybe. Is it? Happens sometimes. It just breaks sometimes. That's better now? Maybe? I don't know. I'm not hearing myself, so I mean, yeah. It usually breaks for just like a couple seconds, I think. Oh.
Doesn't really matter whether it's visited or not. It's about whether the time to that node.
Lead coding until I get a job is what this person is doing. Lead code. Fun. Alright, see you guys next time. Bye.
time, and then add that to the